Alrighty, this is going to be a continuation of the previous video. In this video, we are going to be talking about arc length in terms of parametric equations. I want you guys to think back in AB whenever we did the area unit and we talked about arc length. And we know that arc length is going to be the integral from A to B of 1 plus dy dx squared. Now, unfortunately for us, the bad news is that we don't really have dy dx in terms of parametric equations because everything is going to be in terms of t. So here, if we have a parametric curve described by x is equal to f of t and y is equal to g of t, we can use the chain rule to find the derivative of y with respect to t, since we want that in terms of parametrics. So in order to do that, I have dy dt, and that's going to be dy dx times chain rule dx dt. Now, we are going to be solving for dy dt here just because we kind of want to figure out what dy dx, we want to solve for dy dx here because in my arc length formula, I have a dy dx. So what we're gonna do is use substitution once we find out what dy dx is. Well, if I solve for dy dx, that's just me dividing dx dt with dy dt to get dy dt over dx dt, which, if you think about it, kind of makes sense because if I were to think about this as a fraction, which technically they are not, but if I were to think about this as fractions, notice how the dt's will go away and then you're just left with dy dx. So that's one way to remember it. Now, given that information right here where dy dx is equal to dy dt over dx dt, what I'm going to do is substitute that in right here, and then I'm going to simplify. So what I did here is go ahead and have common denominators. In order to do that, I have dx dt squared plus dy dt squared. Okay, now, no, that's just the xet. I feel like this will cancel out with this right here. So that's how we're just left with dx dt squared plus dy dt squared right here. So this is my formula that we're going to be using. Now, this is going to be very important for us because sometimes my curve isn't going to be a circle. It might be something wonky, or it might be easier if we left it in terms of t in terms of parametric equations so that we don't have to eliminate the parameter. So like number 8 here, where we found that for cosine t and sine of t, that was just a circle which had a circumference of 2 pi. We're going to do it the calculus way, and then we'll see why that is going to be 2 pi. So we are going to have the integral from 0 to 2 pi. We have the square root of dx dt and dy dt. So dx dt is going to be negative sine square of t plus cosine square of t dt. While sine square of t, negative sine square of t, well, let me do this actually. There you go. A negative sine square of t is going to be positive sine square of t. And then this is positive cosine of t. So if I were to do that, that is going to give me cosine square of t plus sine square of t dt from 0 to 2 pi Oh, guess what? This is just 1. So now I have the integral from 0 to 2 pi of 1 dt. That's just going to be t from 0 to 2 pi. That's how I get 2 pi as my answer. Likewise, for number 9, if I want to find the arc length using our formula, we are going to go from 0 to 24 of my dx dt, so my derivative with respect to t. In this case, I'm going to have 10 pi over 4 sine pi over 4t square. Make sure that's negative also, because the derivative of cosine is negative sine. And then we have 10 pi over 4 cosine pi over 4 t square dt. Now, it might look nasty a little bit, but don't worry, because it's going to get a little bit prettier. Now we have from 0 to 24 of 100 pi square 16 sine square of pi over 4 t plus 100 pi square over 16 cosine square pi over 4 t dt. If I factor out the 100 pi square over 16, I'm going to get sine square of pi over 4t plus cosine square pi over 4t. And guess what? That's just going to be 1. So now I'm just left with the integral from 0 to 24 of 10 pi over 4, me simplifying that, dt. I could even simplify that some more to get 5 over 2. And then, of course, I'm going to integrate that. It's just going to be t from 0 to 24. And if I were to do that, 24 over 2 is going to be 12. 12 times 5 is 60. So we get 60 pi as our answer. Now, obviously, this might look like a little bit more work in terms of number 9. But in the long run, it is going to be easier just because our curve isn't going to be a circle most of the time. And it's going to be something weird. So it might look like that. Who knows? All right, so we're going to be doing more eliminating the parameter in terms of trig. This is going to be a lot of fun. So let's say number 13, where we want to eliminate this parameter right here. We have x is equal to cosine of t and y is equal to cosine of 2t. And I gave you a hint that cosine of 2t is equal to 2 cosine squared t minus 1, which is one of the trig identities that you kind of need to know for this class. All right, so if we are eliminating the parameter, that's just me substituting in what I know. In this case, I know that y is cosine of 2t. I also know that cosine of t is just x. So this one here, not that bad. We just get y is equal to 2x squared minus 1. Same thing with 14. I give you the little hint. X is equal to cosine 2t. Cosine squared of t is y. So I get x is equal to 2y squared minus 1. Just kidding. Oh, just kidding. Oh, this is sine, not cosine. Oh, plot twist. Even though I made this question. That's funny. Because we have sine and this is cosine, you also need to think about another identity that we can use for cosine square. Hint, hint. 1 minus sine square of t. Hint. So that's going to give me cosine of 2t is equal to 2 minus 2 sine square of t minus 1. Simplify that. I'm going to get 1 minus 2 sine square of t. Okay, now this looks a little bit better, because then I could say x is equal to 1 minus 2y squared. That's my final answer, I promise. All right, 15. A particle moves in the xy plane such that x is equal to t plus 1 and y is equal to 1 minus 2t squared for 0 to 4. What point corresponds to a local maximum? So far, we don't know anything about the calculus way of parametric equations, but we will eventually learn what to do. But for now, we are going to have to eliminate the parameter because I don't know how to take the derivative of parametric equations. I mean, I do, but find out what dy dx is. Well, maybe we do. Just kidding. We probably do, right? Yeah. Okay. I'm going to show you the eliminate the parameter way, and then I'm also going to show you the calculus way, since we kind of know what dy dx is in terms of what we have up here. For 15, I'm going to eliminate the parameter. I'm going to eliminate the t with x, so that I have x minus 1 is equal to t. Y is equal to 1 minus 2, x minus 1 squared. And then I'm going to take that derivative. Dy dx is going to be equal to negative 4 x minus 1, which means that I have a critical point at x is equal to 1. This is a linear function, and it is decreasing, so I'm just going to draw that as my little sign chart. Positive, negative. So this tells me that I have a local maximum at x is equal to 1. If I have x is equal to 1, then this tells me that y is equal to 1 minus 2 minus 1 squared. That my y value is going to be 1. So my coordinate is 1, 1. Now that was the non-calculus way, the non-parametric way, using calculus and my traditional derivatives. Now we did see earlier that I told you guys that dy dx is equal to dy dt over dx dt. I'm going to take the derivative of dy dt, and that's going to be negative 4t. And then I'm also going to take the derivative of dx dt, which is going to be 1. All right, so we want to make sure that this derivative is 0. So in that case, this derivative is 0 when t is 0. That doesn't give me a lot of information. T is just 0. Well, what I can do now is just plug this back into my coordinate and see what that gives me. Of course, you kind of do want to check for critical points. 0. It's negative. So it's a max. Okay, I forgot to do that. Now, if t is equal to 0, then I'm going to substitute in that here for x and then here for y. And you're going to see that this will also give you 1, 1. So that is the calculus way in terms of parametric equations. And in the next video, which is going to be the next lesson, we'll do more on the calculus way of parametric equations, which means we are going to find the second derivative, we're going to find concavity, we're going to find tangent lines, and all of that good stuff. It's going to be a lot of fun, but that's going to be the next video.